So, Gilles, the floor is yours. Thank you.
Thank you. I did have slides. Okay.
Tonight we have to talk.
Thank you. So
We'll put together lunchtime.
my talk.
I'm free.
Can you hear me? Yeah. Okay. So my talk is about the role and the place of language, logic, formal methods, proof systems, and so on within the general realm of artificial intelligence. Can we see the slide, please? Okay, thank you. Okay, first of all, the phrase artificial intelligence per se is at the origin of many problems. And one of them that it has changed its meaning already twice in 60 years of existence. And when the word was created in the 50s, it mostly designated programs that were able to reason logically. That was later called automated theorem proving. Then in the 80s, it mostly designated programs that were able to use a natural language, which was later called natural language processing. And today, it mostly designates programs that are able to learn. So instead of using the word artificial intelligence, which is at the origin of many confusion, we could use instead the word machine learning. So I'm not going to try to explain what machine learning is, but I'm going to try to be a little bit precise about the question and the problem that machine learning solves. And to do so, I will describe an experiment I did with high school students. So it's not a scientific experiment, but it's a reproducible experiment. So you can do it by yourself with children if you like. So I first showed to the students two pieces of art of the same painter, and here they are. And I gave them the name of the painter, which is on the slide, Ambrogio Lorenzetti. So this is the first piece, and this is the second one. Then I showed them two pieces of art of another artist, and here they are. And I gave them the name of this artist, which is Keith Haring. And then I showed them another work, and I asked them to identify if the artist was either Lorenzetti or Haring. And in fact, they got it right on the spot. So then I asked them, how did you reach this conclusion? If I had never seen any work of Lorenzetti or any work of Haring, could you explain me what is a method to make the distinction between a work of one painter and a work on another? And they were mostly unable to explain anything. So they didn't know how to explain how they were able to identify the artist of this work. They said it's obvious, it's visible, everyone can see it, but there was no explanation on the method. So this was exercise 1. Then came exercise 2. So I asked them to add 98 and 99, and they got the result after a while. And then I asked them how they had reached this conclusion, and the explanation was very clear. They had added the 8 with the 9, and it yielded 17, and they had written the 7 and kept the carry 1 and went on. Okay, so it seems that we have here two kinds of processes. Addition can be qualified as a conscious process, and image recognition as an unconscious process. And here I'm using the adjective conscious. I'm not using any noun, I'm just using an adjective. And I'm using the adjective conscious roughly in the meaning Leibniz gave to this adjective, which is a little bit like the one Freud gave to this adjective later. So the process is conscious if by itself it produces, together with the result, an explanation on how the result was reached. And whether this process takes place in a human brain or in a computer or in nature, whatever, it doesn't matter. What makes it conscious is that it produces something that we recognize as an explanation. And in the case of image recognition, we have an unconscious process, because the process by itself does not yield an explanation of why the artist is this one or that one. But more importantly, and probably this is an explanation of why one process is conscious and the other is unconscious, is that one process using symbols. So it's a process that processes symbols, addition, and the symbols are the 8, the 9, the 7, and the 1, the digit that permits to figure numbers. While in the other, it seems that there is no symbol to process. So image recognition is not an activity where we do process symbols. Of course, people like Stanislas could describe in their own language what is going on in the brain of the child. But this is not the language of the child. This is Stanislas's language. And it means that in the process itself, even if we can externally describe the process with words, in the process itself, there are no words and no symbols. So it seems that we need an adjective to designate these processes that are unconscious and non-symbolic. And I should say they are non-symbolic, hence unconscious. And I suggest that we should resurrect a word that has disappeared from the vocabulary of philosophy and science for long, which is the word instinct. Of course, if you think that the word instinct is too overloaded, we could pick another name. But I should say that image recognition, because it is non-linguistic, hence unconscious, is an instinctive process, while addition is a linguistic process. Okay, well, what does this has to do with machine learning? We have to understand that for long we had a paradox in computer science. It was called, we can call it the paradox of instinctive algorithms. It is that because it's a linguistic conscious process, its addition is easy to program. It's not difficult to write a program that performs addition. But because it is instinctive, image recognition is difficult, is more difficult to program. And for long, we didn't know how to program it. So when we taught computer science to the students 20 years ago, we said we can build a computer that add two numbers of 1 million digits, which seems to be difficult to do for us. 1 million digit is a lot. When you want to add that, probably you will make a mistake at some point. But although we are able to program computers to do very difficult tasks, such as adding two numbers of 1 million digits, we cannot program a computer to recognize a cat from a dog, although it's a childlike simplicity. And this is this problem that machine learning solves. And here is one possible solution. You have first to define a metric that measures the similarity between two images. So it's not so easy, but it's not impossible. You can define such metrics. It takes some time, but you can do it. Then you can look at the 5 pieces of art I showed you, and you see that the unidentified work is closer to the 2 works of Haring, and it's further apart from the 2 works of Lorenzetti's. So you can say that statistically, it is more likely to be a work of Haring than of Lorenzetti. And this is how machine learning algorithms work. So this is a specific machine learning algorithm here. There are other algorithms, but more or less, they all work the same. Of course, if we go to the details, they are very different. But if we look them from sufficiently far, they all work like this. And they all are based on this idea that everything that looks statistically like a dog is likely to be a dog. And this is why, how machine learning algorithms work. And probably we can say that all of them have this assumption that something that statistically looks like a dog is likely to be a dog. okay, when we reach this conclusion, there is a question we cannot avoid, is why do we need languages after all? Why do we need language after all? Because we have these instinctive algorithms that we are able to program now, and they solve many problems without manipulating symbol and without being able to explain what they did. So we cannot avoid this question, is language useful to anything? And I think it's an important question, for instance, for this kind of debate, because it's not only transhumanism that is, transhumanism is not the only philosophical question which is raised by the development of machine learning, but also this question of the place of word in the world. So one reason why we need languages is that in some cases we want an explanation. So for instance, we want to explain eclipses, not just to predict them. So it's maybe possible to train a machine learning algorithm to predict eclipses. In some sense, the Ptolemaic model was very good at predicting eclipses. It could be seen as a well-trained machine learning algorithm able to predict eclipses. But it's not just what we want. We want also to explain eclipses if we can. If we cannot, it's already good to predict them. But if we can, we want to explain that the shadow of the Earth and so on. Okay. Then there is another reason, which is that it's not always the case that everything that looks like a dog is most likely to be a dog. And I gave here 3 examples. It's not the case that what looks like a correct mathematical proof is a correct mathematical proof, because incorrect mathematical proofs very much look like correct ones. It's very difficult to spot a mistake in a mathematical proof. And very often, when you just have a look at it, it looks like it's correct, then it happens to be incorrect. It is the same for Turing machines. A non-terminating machine sometimes looks like very much a terminating one. And it is the same for a problem which is very important in computer science, which is the problem of correctness of programs, the absence of bug. And many incorrect programs look like correct ones. So it means that we are not sure that with machine learning algorithm we could solve these kind of issues, such as the correctness of the mathematical proof, the termination of a Turing machine, or the bug-freeness of a program. And if we take this assumption, it means that we need both machine learning, we need both instinctive algorithms and linguistic algorithms. We need some algorithms to recognize a cat from a dog, or a work by Lorenzetti from a work by Haring, which are instinctive algorithms. But we also need linguistic algorithms, for instance, to check the correctness of a mathematical proof. And if we want to give names to these 2 branches of computer science, a branch that studies instinctive algorithms and the one that studies linguistic algorithms, we could call the first one machine learning and the second one formal methods. Of course, it's a bit rough classification. We could go further in the details, but let's say there are 2 parts in computer science, machine learning and formal methods. So is it what computer science looks like? You have machine learning on the left, you have formal method on the right, and these people don't talk much one to the other. And I think it is not the case, and because it's not, of course, instinct and language are very different, but they can work together. So what does it mean? It means, for instance, that I said that the correctness of the mathematical proof cannot rely on instinct. So machine learning is not good, as far as we know, to recognize the correctness of a mathematical proof. But the heuristic to find a proof is very instinctive. So for instance, take a primary school geometry problem or a middle school geometry problem. If you have 2 perpendicular lines, it's your instinct should lead you to use the Pythagorean theorem. If you have two parallel lines, your instinct should lead you to use the intercept theorem. And this is a very instinctive process which we learn and that machine can learn, but it has nothing to do with the correctness of the proof which is built in the end. It is just a heuristic to build the proof. It is also the case if we move from epistemology to ethics, because probably we cannot sentence someone in court because his case statistically looks like those of many convicts. We cannot say to a defendant, you look like someone we already put in jail, so we are going to put you in jail as well. Maybe from a purely consequentialist point of view, this can be defended, but I don't want to defend this point of view today. What we have to do at least is to explain the judgment by giving the law article on which it is based. And this law article by itself is linguistic. So we have to, even if we are using machine learning to judge defendants, to judge accused people, which is a separate discussion. I don't want to go in this discussion, but even if we do, then we have to provide an explanation, and this is what is called today explanatory AI, because we cannot just sentence someone on the idea of a similarity of the two persons or even of the two cases. And I think that this means that in computer science we have to reconcile instinct and language, and I think that this project goes much beyond the computer science. We can say that in the world that we live in general, it's one of our challenges today is to reconcile instinct and language. Thank you.